In this screencast, we're going to show how adding an additional pipe to a system changes the flow rate. So we'll start by calculating the flow rate between two tanks that are connected by a single pipe as shown here. So we'll start by simplifying the energy equation. So here our P is equal to pressure. Our gamma is equal to specific weight, which is the same as density times gravity. Our V is velocity. Our G is gravity. And our Z is the height measured from some origin. So how can we simplify this? Well, looking at this indicates that it's at atmospheric pressure. Therefore, we can say that P1 is equal to P2, which is equal to 0, where this is 1 and this is 2. In addition, because you have a large reservoir diameter going into a smaller diameter, you can say that the velocity at the top is equal to 0. So V1 is equal to 0 and V2 is equal to 0. And so then we have that Z1 is equal to 25 feet and our Z2 is equal to 0. And so what we're left with when we simplify that is that our Z1 is just equal to this H sub L, which is the head loss, which is equal to the friction factor, the length of the pipe divided by its diameter, the velocity in the pipe squared divided by 2G. And so if we write that out, we have that 25 feet is equal to, and if you notice here we're given the friction factor, so that's equal to 0.02. Friction factor is unitless. Our length is 1,100 feet, and we divide this by the diameter. Be careful, that's in inches. You want it in feet. And then what we're looking for, the velocity of the pipe squared divided by 2 times gravity, which is 32.2 feet per second squared. And so when you do the calculations, you find that the velocity of the pipe is equal to 6.05 feet per second. But what we're looking for is the flow rate, or Q. So Q is equal to the velocity of the pipe times the area of the pipe, where the area of the pipe is equal to pi times d squared, 0.5 feet squared, divided by 4, which is equal to 0.196 feet squared. And so our Q, with this single pipe, as shown here, the flow rate through that pipe is going to be equal to 1.19 feet cubed per second. Now, let's add a second pipe and see what the percent change in flow rate is. So for our second system, we're going to have here a Q1, and here's Q2, and here's Q3. So Q1 is going to be equal to Q2 plus Q3. We can also write this in terms of the continuity equation, such that V1A1 is equal to V2A2 plus V3A3. So let's do two energy balances. One for the fluid that goes through pipe 2 and the other for the fluid that goes through pipe 3. So we have the same simplifications that we had before, where the pressures are equal to 0, where the velocities at the top of the tanks are equal to 0, and that our Z is equal to 25 feet. So we'll write the first one. So our 25 feet is equal to the head loss through the first part of the pipe plus our head loss through the second part of the pipe. And that's if we're going through here. Now we'll take a look when we go through pipe 3. as well. So this is 25 feet. Same thing. First we go through the first part. F1, L1 divided by D1, V1 squared over 2. But now we add to it the head loss in that third pipe, L3 over D3, V3 squared over 2, and these 2's should all have gravity multiplied by them. And we will assume that the friction factor is the same for all of these pipes and equal to 0.02. So for our second equation, we're looking at here and the head loss here. So since we're looking for Q1, what we want is to find V1. So let's write these two equations in terms of V1. So that first equation, putting numbers in, we have 25 is equal to 0.373 V1 squared plus 0.31 V2 squared, and therefore we can write V2 is equal to the square root of 25 minus 0.373 V1 squared, and we divide that by 0.31. Now let's do it for the other pipe. So we have 25 is equal to, again, because it's that first pipe, 0.373 V1 squared plus now 0.235 V3 squared. And now, and let's skip a line down here to make it a little neater, our V3 is equal to the square root of 25 minus 0.373 V1 squared. Again, we're writing everything in terms of V1, and this is divided by 0.235. Now, let's put this into the continuity equation. And if you remember, that's V1 A1 equals V2 A2 plus V3 A3. So we're going to put the V2, which is a function of V1, into there. We're going to put the V3 into there, and then calculate the areas where the area is equal to pi times the diameter squared divided by 4. To solve this, you're going to have to use some kind of root finding program. What I used was Solver, and the answer that I got for V1 is equal to 8 feet per second. Again, remember we're looking for Q1, so that's equal to 8 feet per second times the area, which we already calculated before, 96 feet squared. And so our Q1 is equal to 1.57 feet cubed per second. And finally, what we need to do is find the percentage change, or in this case, the percentage increase in flow rate. So that's going to be equal to our 1.57 minus our 1.19, which is the flow rate we got from the single pipe, divided by 1.19, and these are all in feet cubed per second, and this is equal to 0.32 or 32% increase. One thing to take note of is that this problem is very sensitive to rounding errors.